In this presentation, we're going to write some C++ code to implement a graph as an adjacency matrix. As you recall, a graph is a collection of nodes or vertices that are connected in almost any way you can think of via edges or paths. Here we can see what we call an undirected graph, where it's assumed that since there are no arrows, we can go either way. We can go from A to B or B to A. And here we have a directed graph where you can only go from A to B because of the arrow. The adjacency matrix is just a two-dimensional array that stores a 0 or a 1, indicating whether a path exists or not. So for example, there's no path from A to C, so we have a 0 entry there because we don't have a path from A to C. So we're going to write some code today to implement a graph as an adjacency matrix, or how it uses the underlying storage mechanism as an adjacency matrix. And instead of a simple two-dimensional array, I'll actually use a vector of vector, so that it'll make it easier for the graph to be modified. We can add more nodes, add paths, remove nodes, and so on. Some of the capabilities that we want for a graph is to be able to insert, remove, and search for a node, and to be able to insert, remove, and search for an edge, and then just to print out the graph, and we'll print it out as an adjacency matrix in this case. Some of the things that we'll need, since we're going to be using a two-dimensional dynamic array or a standard template library, a vector of vector, we recall we need a little bit of review on some vector capabilities. So we know that we can add an item to a vector using pushback. We know that we can use iterators to loop through a vector, and we can declare those iterators with the auto keyword. We know that there's a begin and end iterator that marks the beginning and end of the vector list. We can dereference an iterator with the dereference operators. There's also an erase method for vectors that allows us to remove an item at a particular location. So we can look this up in the documentation and actually see examples of vector erase. So if you pass in a single iterator position, it will remove that single element. Or if you pass in a range from beginning to end, it'll remove all the elements, or some in between depending on the range that you pass in. We've seen also that there's the standard find function that I believe is in the algorithm header file, and we can use that to search in an array to try to find a particular value, a particular item in the vector. So these are some of the STL vector capabilities that we may need when we're writing this graph implemented as an adjacency matrix. So let's go ahead and get started. I've got an empty project here, and just to make it easier for the presentation, I'm going to put all the code in a single file, a single C++ file, and I'll just call it adjacency matrix graph.cpp. Just to keep things simple, I'll just make everything public for now. So I'm going to have two major pieces of information here. The first is I'm going to create a vector of string that stores all the nodes of the vertices. So these strings are going to be labels like letters A, B, C, D, or maybe city names, whatever we want to label the nodes of the vertices. So I guess we need some include files. To be able to use the vector and string capability. We may need more. I think for find we need algorithm. For formatting the output, we need this IO manip. We'll see. Maybe we'll need some others. We'll see. So there's the list of the nodes, the names of the nodes of the vertices. So they will be the labels. When we print it out, they'll be the labels that we use on the rows and on the columns. So now the next part we need is the actual adjacency matrix. And again, I'm going to use a two-dimensional dynamic array. So it's going to be a vector of integer. So because I have a vector or nested, it's going to allow for essentially a dynamic two-dimensional array. So we can put some comments in here about what some of these things are. And one thing to keep in mind is that in the adjacency matrix, each row, there'll be as many rows in this matrix as there are nodes in the label list. So every node that we have will have a row, and then for each row, the number of columns on that row will also be the same, because the adjacency matrix will always be square. Okay, so now we're ready to put in some of the methods that we might need. And again, we want to be able to insert, remove, and search for a node. So to insert a node, we'll pass in the name of the node, and we'll ask a question. We don't want to insert a node that's already there, so is the node already in the graph? And we do this with the find method. So we're going to look from node list begin to node list end, looking for this particular name. And if the find function returns the end of the list, then that means it wasn't found. So we're going to go ahead and add it. Now, when we add a node to the list, then our adjacency matrix will no longer be of a proper size. So remember that the number of rows in the adjacency matrix and the number of columns in the adjacency matrix has to be the same as the number of labels or the number of names in the node list. So this brings up another capability that we'd like to have, and that is to be able to resize the adjacency matrix. So this is the dynamic capability that we need. And as we saw earlier with dynamic arrays, when we resize the array, the basic idea is to create a new matrix in this case, resize it, copy the values from the old one to the new one, and then get rid of the old one. We don't have pointers and dynamic memory for our matrix variable, but that's handled internally by the vector class, so that'll help a little bit. So the basic idea then is we want to store the current matrix make a copy of the current matrix and store it as in a temporary location. In this case I called it old matrix. And then we want to resize the current adjacency matrix. So we're storing out a copy of the old one, resizing the current one to whatever the new size that gets passed in. And we're using a form of this constructor. So remember, our matrix is a vector of vectors. So you can think of it as a vector of rows or a list of rows. And we're using a form of the constructor where we say this is the number of rows that we want, and we want each row to be like this. So each row is going to be another vector event with the same size so that it ends up as a square 2D matrix. And we're going to initialize every value on that row to the value of 0, meaning there's no connectivity, no paths at all. So this is the form of the constructor for a vector where you pass in a size and you pass in what every element in that vector is going to be. So every row in the vector is going to be another vector event, the same size so that it's square, and every item 0, indicating that there are no paths currently in there. So now the next part then is to copy the old values into the new values. And we're going to do this with a nested loop because it's a two-dimensional array. And the outer loop is going to go down the row. And it's a little bit odd syntax. I'm using this size t because that's the data type that the vector size returns. And if we have to take into consideration that when we do a resize, the graph may be getting larger, but it also may be getting smaller. We may be removing a label from the node list, and so the graph might get smaller. So it could be that the new size is actually less than the old matrix size. So we want to loop from 0 to the smaller of either the new size or the old matrix size. We don't want to, we have to make sure we don't go out of bounds, so we're going to loop to the smaller of the old matrix size and the new size. And this loop steps down for each row, and then we're going to do something very similar, step across each row for each column, and then we're simply going to write that we want the new adjacency matrix that we resized here, sub-row, sub-column, so it's a vector of vector events, so we can treat it as a 2D array, equals the old matrix, sub-row, sub-column. So we're just copying in the values from the old matrix to the new matrix. And this is our resize operation that we need to perform whenever the node list changes. So since we have inserted a node here, then we should resize graph so that it has the same width and height as the number of labels in the node list. Alright, so now the next part is we might want to remove a node. And so the first thing we want to do is to do a search and only remove the node if it exists. So we do a find again, a search from the beginning of the node list to the end of the node list looking for the names. It's the same thing as here, but we're going to store it in an iterator because we might need that later to actually remove it. But we want to test to make sure that IT is not equal to node list end. So if for some reason we're asking to remove a node that's not in the list, we don't want to do anything. That doesn't make sense really. So maybe we should print out an error message. Some type of error message here. And we forgot an include for cout, which is IO stream. So if the node that the name of the node that we're asking to remove is in the list, then this iterator won't be equal to the end of the list. It'll be equal to somewhere in between, some particular location. And we need to find the index of this, the actual integer index. And you can do that by subtracting the iterator from the beginning of the list. So the subtraction operator is overloaded so that you can subtract the beginning of the list from an iterator, and it will convert that into an index, a numerical integer value for you. So we need the index of the iterator as well. And the reason for this is that we need to remove all the columns in the adjacency matrix and the particular row in the adjacency matrix that are associated with the node that we're removing. So what this means is if we were to remove node D, then we would need to remove this entire row and we would need to remove this entire column. So because we have a nested vector of vector, removing a row is a single step, because that's the outer container. Remember, we have each row is a list of integers, so the outer container is all the rows, and that's relatively easy to remove. The inner container, or each row, has a collection of columns, so to remove all the columns we're going to have to go through loop through each row and remove all the columns. So to remove the columns, at a particular index, we're going to do a range-based for loop. So we're going to go from each row, which is a vector of integer, so I'm using the auto keyword, and I'm also making it a reference because we want to change it. So for each row in the adjacency matrix, I want to erase a value on that row. And the value on that row is, or the position on the row that we want to erase is the beginning of the row plus the index. So for example, if we wanted to delete all the columns associated with the node D, then we go through each row. Well, first we do a search and find that D has an index of 0, 1, 2, 3. Then we iterate through each row and we remove or erase the value, the item in that list whose position is beginning plus index, which is 3. So here's the beginning, plus 1, plus 2, plus 3. This is the position that we will be erasing for each row in the adjacency matrix. And that's what this for loop does here. And notice that we need the index in order to offset from the beginning of the row. So that's why we computed it here. So that's the harder part. The easier part then is we want to remove the entire row. So here we removed all these columns. Now we want to remove this entire row, and because that's part of the outer vector container of the adjacency matrix, that's just a one-line item there. And it is the adjacency matrix, which is a list of rows. We want to erase the row whose label was D in the example we're looking at. And that's simply going to be the adjacency matrix begin plus index. So this is going to remove the row at a particular index. So in the diagram here, we want to remove this row associated with D. The adjacency matrix begin is the first row. The index or offset was 3, so this is offset 0, offset 1, offset 2, offset 3. We're going to erase from the adjacency matrix the beginning of that adjacency matrix, the first row plus the index or offset, which was 3. And so that particular line of code removes the row at that index in the adjacency matrix. And then the last thing we want to do is actually remove it from the node list. So where is it in the node list? And we can do that with the node list dot erase, and we want to erase at a particular position. And we could either put node list dot begin plus index, that would work, or we could write, just pass in the iterator position. So that's the code involved in removing a node. It's not enough to just remove the node from the node list. We also have to modify the adjacency matrix as well. The next thing we might want to be able to do is to search for a node to see if it's in our graph. And signature for that may look something like this. So we want to pass in a string and look through the node list to see if it's in there, and if whether it is or not, we return an iterator for that particular vector of string. And this is just simply calling and returning the results of the find function, and we've seen this before. We called ours node list. So that allows us to insert a node, remove a node, and then also search to see if a node is in our graph. So now the next step, we may want to insert edges into our graph. And for an adjacency matrix, inserting an edge is just a matter of replacing a 0 with a 1. The challenge, though, is which one of these zeros do you change? And to figure that out, we need to find the index of the row and the index of the column. So we need 2 dimensions because it's a 2-dimensional array essentially. So we need to find the index of the row and the index of the column. So the signature for inserting an edge may simply be just the name of the from node and the name of the to node, so the name the node that we're going from and the node that we're going to. And so notice this is going to be a directed graph. And we need to make sure that both the from nodes and the to nodes are in the graph. If they're not, we may get an out-of-bounds problem, may get an index. And we can decide if we want to. It's up to us on this application, but in this particular case, I'm going to make a decision that if either or both of the nodes are not in the graph already, then I'm going to go ahead and insert them. And so what that'll allow me to do is to write a simple statement like graph.insertEdge A to C. And even if A or C or both of them are not already in the graph, it'll go ahead and add them to the node list, change the size of the adjacency matrix, and then add the path from A to C. So instead of producing an error message if I'm trying to add a edge whose endpoints, one or more of the endpoints doesn't exist in the graph, instead of printing out an error message, I'll just go ahead and add that vertex or that node to the graph, and maybe both if neither of them exist. So then we're going to do a search to see if the to node is in the graph. And if it's not, then we're going to insert it. So if the node that we're going to is not in the graph, then we're going to insert it. And then we're going to do the same thing for the from node. Now that we know for sure that the to node and the from node are both in the graph, then we can insert the edge using the indices. So we can calculate what I call the from node index, and that's going to be the row. So we decided here that the from nodes are going to be the row, 0 row, 1 row, 2 row, and so on. And we can calculate that as the from node index, the iterator that we get from our node list minus the beginning of the node list. So basically we're calculating that index as, so say we want to insert a path from D to C, we're calculating that index as search for the D and find its iterator, and then subtract the beginning from it, and I would get 1, 2, 3 as the index there. We'll do the same thing for C, search for that in the node list, subtract the beginning iterator, and I would get 1, 2 for the index of the 2 node of this particular path that we're inserting. So then the 2 node index is the same thing, except it's the 2 node iterator minus the beginning of the node list. Once we have that, then we can index into our adjacency matrix, and remember that the from node is the row and the to node is the column, and that's just a decision that we made. The from node is going to be what particular row, and the to node is a particular column. So we're just going to index from node, to node, and what value do we put there? Well, if we're inserting a path, we're replacing a 0 with a 1. We're putting a 1 there. So now a path from the from node to the to node exists in the adjacency matrix. So this is inserting an edge. We may also want to remove an edge, and the signature for that may look something like this. We pass in, again, a from node and a to node, and we want to replace that edge or that path with a 0, indicating that that path no longer exists. First, though, we want to make sure that the from node is in the graph, and if not, we might want to put some type of error message. So if the from node is not equal to the node list dot end, that means that the from node exists in the graph. We need to do the same thing for the to node. And we want to ask, is the to node not equal to the node list end? So is the to node in the graph? And if both of these conditions are true, so if the first if passes, that means the from node is in the graph. If the second if statement passes, that means the to node is in the graph. And then since they're both in the graph, then we can actually do a removal. And remember, removing a path is just the same thing as inserting it, except instead of using a 1, we use a 0. So we compute the to node index and the from node index the same way we did before, just by searching for it in the node list, getting its iterator, and subtracting it from the beginning of the node list. Once we get those indices, then we can index into the matrix and set that edge to not existing, put a 0 there. The other thing we may want to do is to do a search for an edge to see if a particular edge exists in the graph. And the signature for that may look like this. Again, we're passing in the name of the node we're coming from, the name of the node we're going to, and we'll return a Boolean, a true or false, indicating whether that path exists or not. And we want to do the same thing, very similar thing that we did here, where we check to make sure that the from node exists, and then we also check to make sure that the to node exists, because we want to make sure we don't index out of bounds. And then we want to return a true value if that particular path has a 1 and not a 0. So the value of a location in the adjacency matrix represents a particular path. And if it exists, that value will be a 1 rather than a 0. So again, we can compute the indices of the from node and the to node, and we know they'll be legal indices because we've already asked if the from node is in the graph and if the to node is in the graph, and we got true for both of those. So we know it exists, we know those will be legal indices, and then we will return a true or false. And we want to return true when the value in the adjacency matrix at those indices equals 1. That means the path exists. If for some reason neither of these if statements pass, that means the nodes were not found in the list, in the graph. And if the nodes are not found in the graph, then there's no way that that path can exist. So we'll just return a false. So we're making good progress here. I know it's taking a little bit of time, but we have the ability to insert a node, remove a node, search to see if a node is in the list, in the graph, insert an edge, remove an edge, and search to see if an edge is in the graph. And we added one additional function here that can resize the adjacency matrix, and this needs to be done whenever a node is inserted and then we did a slightly different version of the resize by erasing columns and rows when a node is removed. So one of the last things we might want to do then is to print out the graph so we can see it. And maybe the easiest way to do it is just to print it out as a 2D matrix like this with labels across the top and labels going down the side. So we'll just have a print method or display, or maybe even a toString method that returns a string that we can print out. Different ways of doing this. And a couple of things we may want to do. First is we know that the matrix is going to be square, so it might be useful to store the size of the node list, and maybe we call this num nodes or num vertices. And then in order to print this out neatly so columns line up and we have spaces in between, we may use the set W from the IO manip when we use cout, and that will allow us to set up a field of 4 or 5 spaces and print everything right justified so all the columns will line up nicely. So I'll set this field width variable to 5, and we can change it if we need to. If for some reason our node names become city names, then we may need a larger field width or something. So we're going to start out by printing out the columns at the top. So let me just, I'll move this over here. So we want to print out the columns along the top here, the A, B, C, D, E, or whatever the nodes are. So we just need a loop that starts out by, before the loop starts, we print out a space in the field width, and that's going to account for the row label extra space that we need here in front of the row label. And then we're going to loop from 0 to the number of nodes, and every value in the node list, we're going to print it out in a field of 5 spaces, right justified. And when we finish printing out the labels on the top line, we'll print out a return. So then the next thing we want to do is to start the matrix itself, but remember that in front of every row we need to print out a label. So the row loop might look something like that, but then we don't want to forget the row label, and this is going to be the same thing as the column label, except we're stepping down the row. Now we're ready for the column loop inside of here. So we're ready for a column loop that will step across the row and print each value out of the adjacency matrix. And we're going to use the same field width, but instead of printing out the labels from the node list, we're actually going to print out values from the adjacency matrix. Sub-row, sub-column. After we've printed out each row, we need a return to move us down to the next line. So printing out the matrix with the labels, it's a convenient thing to store out the number of nodes so we don't have to write this every time we need it. And we set up a field width as a variable so that if we need wider columns or wider formatting fields, we can change it easily. And then we print out these columns on top, A, B, C, D, E, starting with a blank to account for the row labels that we want to skip over. So we print out just a space in the same field width, you won't see anything. And then for column equals 0 to num nodes, we print out the labels in the field width, so that gets us the column labels. And then we have the nested loop here for row equals 0 to num nodes, for column equals 0 to num nodes. And before we actually start the column, we print out, or before we actually start the row, one column at a time, we print out the row label. So we print out the row label, then start the column loop and print out each column in that row. And it's either going to be a 0 or 1 that's going to be printed out here. And of course at the end of that row, print out an endo. Well, let's see if we can create a graph. And maybe I'd like to create this particular graph here. And this is an undirected graph. So we have 1, 2, 3, 4, 5, 6, 7 edges, it looks like. because each edge is non-directional, we need to duplicate them all, so that's going to be 14 edges in the graph, I guess. So let's see if we can do this. So I'm going to say, maybe we'll start off simple. So we'll say create our graph, and then graph dot insert edge, and remember that, and we need an edge from A to B, and remember that insert edge searches to see if A and B are in the graph, and if they're not already in the graph, it goes ahead and adds them. So we insert A and B, and then maybe we'll insert A and C. And to duplicate A and B, we need to also insert B and A so that we can go either way. And let's just leave it at that for now, just for testing purposes, and see if we can print out the graph. See if it'll compile and run it all. So here's our graph so far, and we didn't quite get the columns in order. It doesn't, the order of, it doesn't have to be alphabetical order, but we know we have an edge from A to B, so here's our edge from, and remember the from is the row, so here's A to B. And we also have an edge from B to A, so this is B to A, that's that one. And then we have an edge from A to C, that's this one, and all the rest are zeros. So it looks like it's beginning to work. So let's go ahead and fill them in. We've got A to B, B to A to C, C to A, and A to D, and D to A. So those are all the nodes that are related to A, or all the paths that are related to A. So it's 1, 2, 3, 4, so that should be 8. 1, 2, 3, 4, 5, 6. Oh, we forgot one. What are we missing? We have A to B, A to C, and A to D. Oh, okay. So I actually counted B to C, and I shouldn't have done that. I shouldn't have counted B to C. So let's do that now. We're going to do the B to C and C to B, and then let's do B to E, and then E to B. So now the only ones that left, I guess, are D that we haven't done. So we need D to E and E to D. And then we need D to F and F to D. And so this gives us, should be 1, 2, 3, 4, 5, 6, 7 times 2. It should give us 14 paths, so that we have an undirected graph, and then print them all out when we're done. So let's see what we get. So again, the order wasn't necessarily in alphabetical order, and that's not critical, but we should be able to find all the paths that we have in here. For example, we have a path from D to A, so we go down to the row D to column A, and that gives us a 1. And we have D to E, so we go D to E, and I won't check all of these, but just verify a few. We have a C to B, so here's C to B, and it's there as well. So we do have to go through and verify them all, but it seems like it may be working. So in this presentation, we built some graph code that's able to insert and remove edges from a graph that's using an adjacency matrix for storage. Now let me know if you have any questions on this.